I think I heard a beep. I will begin. Heavenly Father, we thank you for this day. We thank you for the break, and just ask that you bless our work for the remainder of the semester. To just pray that you encourage the students just to continue try to do their best each day, Lord, and that you'd help them to just correct whatever things they overlooked for the first test. There's still time to fix things, and just pray that you'd encourage them to work on this course and to fix whatever it is that they don't understand, Lord. In your name I pray. Amen. Okay, so yeah, I mean, some people missed some problems on the test. We'll talk more about that later. Let us forge ahead. So what's next in this course is a discussion of what are known as energy methods. And energy methods are so very, very nice. So much nicer way of thinking about things. And so let's talk about this. So energy, let's just have a discussion about energy as a more general concept here. So what is energy? I mean, people talk about sending your energy out into the universe, right? There's the use of the term energy as promulgated by folks like Oprah, right? The church I used to go to in Raleigh, pretty much everything the pastor would talk about, he would always bring it back to contrasting the scriptural view against what Oprah says and expose her for her various forms of heresy, whether it is using Jesus as a metaphorical construct or whatever, as opposed to the literal Son of God, whom some of us believe in. Now, energy is something much more specific than some sort of cosmic, out there, fuzzy idea. It's a specific physical object. There's different kinds of energy. There's mechanical energy. There's potential.
My name is Kathy Lawson.
It is Oprah.
I've offended the great and mighty Oprah. Yeah.
She's coming up. Where did that come from?
Huh. I wonder what the way to fix that would be. Well, I guess we're going to be okay. It's not continuing, right? One of you doesn't. It wasn't like one of you like throwing your voice or something, like, right? I mean, okay. All right. Sorry. This brings me to an important point. The next test. If you would like to bring music to listen to while you're taking the test, you're welcome to do it.
Sure.
Yes. Yeah, I mean, take me out of the ball game. Could have significance to a problem on your next test. It's possible that you have a baseball question, but we can't bank on it being that song exactly, right? So just in case it helps you to have some kind of, music to work to, feel free to bring music and listen to it. I don't mind. All right? So you can have your phone out for listening to music, but I would just ask that you not be using your phone for searching things on the test, right? This is forbidden. This is not an LUO test. All right, so. All right. Energy methods. So there is mechanical energy, but yeah, potential energy of various sorts and flavors we'll talk about. There's chemical energy, electrical energy, and I talked about the first day, and I think the gentleman who talked to me a lot the first day is gone now. Oh. Oh well. So it's unfortunate he didn't make it to this day, because this is the day we really talk about that a little bit more substantively. Not for too long, but we talk about the four forces: the gravitational force, the the weak force, the electric force or the electromagnetic force, and then what's the other one? Gravity, weak, electromagnetic, and the other one is the so-called strong force, right? Now, if you ask me, okay, so what's the formula for those forces? I wouldn't know, And it's not just because I'm not an expert in nuclear physics. It's because nuclear physicists don't think in terms of literal force. They don't think about F equals ma. What we think about as you go on in physics and study more deeply is momentum and energy. This is what modern physicists use to study matter. Momentum and energy. So it would probably be more accurate to, instead of saying the four forces, to perhaps say the four energies. Because that's really more what it is. There's a sort of potential energy of some sort or another associated with each of these different quote-unquote forces. So there's a weak potential, there's a strong potential, anyway, we don't have formulas for those, and we wouldn't try. Those properly fit in the context of a larger discussion of something called quantum field theory. And that, of course, is not something we're going to talk about in here. That's like quantum mechanics for fields. But anyway, for us, the energy method is going to concern, this is, classical energy. And for us, we're thinking about mechanical energy. And the mechanical energy, at this point, is going to have two pieces. It's going to have the translational kinetic energy, and it's going to have a potential energy. So this is essentially at energy, which we'll use E for, is equal to kinetic energy plus potential energy. Now, the form of the kinetic energy, that's always the same for the problems we work. Kinetic energy is always just 1/2 mv squared. So that's 1/2 times the mass times the speed squared. All right? On the other hand, the potential energy, this has many flavors. There are many flavor choices. And that will depend on the problem we're working on, the specific form of that, all right? Here's a few different choices. One, the first thing we'll talk about is potential energy is mgh. This is the potential energy due to gravity near the surface of the Earth. It's mass times gravity times height gives you the potential energy due to gravity, all right? If we're talking about gravity and we're not near the surface of the Earth, but we could be near the surface of the Earth, or we might be far away, then the formula which takes over is big G, goodness gracious, now I've forgotten. I think little m, big M, divided by the distance. So this would be the potential energy due to gravity more generally. So the thing is that the connection between these two ideas is just that if we put, to get from here over to here, if we put the radius equal to the radius of the Earth, then what you find out is that G times the mass of the Earth, if you calculate G times the mass of the Earth divided by the radius of the Earth, you know what that works out to? Well, let's work it out. You guys, maybe that's a good exercise for us to do if we haven't done it already. What's the mass of the Earth? We could look it up, yeah? Do you guys remember? I don't remember. 6.667 times 10 to the what? Oh, you are giving me the big G, and that's fine. That's built into my calculator. It's number 39, I think. 6.673 times 10 to the minus 11, that's big G. What's the mass of the Earth? Is it 5.94 times 10 to the 24th? Sad that I know that. Not really. And then what's the radius of the Earth? What was it? 6.37. 5.972. Did I say that right? I said 5.94. Oh, man. Curses. Now I've lost my place. I'm trying to calculate what's the gravitational constant times the mass of the Earth divided by the the average radius of the Earth? What's that work out to?
The Earth is 5.94 times 10 to 24.
Okay.
And the radius is 3,900.
5.94 times 10 to the 24. Yeah, times the big G. Yeah. All right, and then divided by, what was the radius of the other thing again you guys told me?
3,959 miles.
No, I need meters.
Meters?
Yeah.
6.376.
All right. Oh. It's not working out like I was expecting. I'm forgetting something, guys. I'm sorry. These two formulas for potential energy should just agree when we compare them. I'm an idiot. I'm sorry, guys. To compare these two formulas, I probably need some calculus stuff, which you probably don't want me to get into. So the rate 1 over. I think the reason I'm neglecting math and it's caught up to me. 1 over the radius there is 1 over. What's the relation between this r and the h here? Here's a picture. So the radius of the Earth is this, all right? And if we're talking about m out here, h is the altitude actually, okay? H is the distance from the surface of the Earth to the mass that we're calculating the potential energy for. So this right here is h. So the little r is just the distance from the center of the Earth to the point we're talking about. And so this little r is actually the radius of the Earth plus h. And so math. Yeah, I need math to connect these two ideas, unfortunately. And so I will just do it. Actually, you know what? I'm not going to do it. So there's a calculus reason that these can be compared. And this will reproduce that if we look at h being small enough. Oh, fine. You talked me into it. This is 1 over the radius of the Earth times 1 plus h over the radius of the Earth. And then there's something called the geometric series, which I have taught in, whatchamacallit, what's that course called? College algebra. I taught geometric series in college algebra when I first started working here, because I'm an idiot. And anyway, so this piece right here, this h over r, radius of the Earth, is the piece which produces that. And so to understand the connection between these two, I actually have to calculate g times the mass of the Earth, and I need not just one, see, I end up with a radius of the Earth times radius of the Earth. I actually have to look at this squared in order to make the connection, because of this times that is how they match up. I don't know if you can see it or not. If you can, it's not a big deal. This is math you're not responsible for, so sorry. But what happens if we look at g, mass of the Earth, divided by the radius of the Earth squared? What's that work out to? What was the radius of the Earth again? 6.3 times 10 to the... I get 9.77 meters per second squared. Does that look familiar? It ought to. That's gravity. Now these formulas are not directly comparable, all right? So like the potential energy, the MGH formula, this makes potential energy be 0 at the surface of the Earth, right? If we use this other potential energy formula, what's the potential energy at the surface of the Earth with the right formula? It's not 0. It's what? Like here, we have potential energy equal to G times the Gm, big M, divided by the radius of the Earth, right? Which, of course, is not equal to 0. So these formulas are related, but they're not the same. And this is bringing up one important point that I should share with you about potential energy, which is that it's not uniquely defined. So you can reset where you want to make the 0 for potential energy to be different places as we work problems. Right? I could say that we're in 0 potential energy right now here on the 4th floor of DeMoss. But somebody else might say, no, no, no. You've got potential energy. If I could somehow drill a hole in this floor, right, you'd fall down and you'd gain kinetic energy as you fell because you'd be converting that potential energy into kinetic energy. And when I hit the 3rd floor, I would stop and then I have 0 potential energy. So like another person could say, oh, well, the potential energy is 0 on the 3rd floor, right? You can pick any level that you want to define to be the 0 of potential energy. There's an ambiguity in that sense. I'm just trying to tell you, these two are two different formulas for potential energy, which each have their place. Which one should be used for a problem about a satellite, which is like in geosynchronous orbit? We use this one, right? If we're talking about things far away from the surface of the Earth, this is our guy. If we're talking about inclined planes, stuff that's close to the surface of the Earth, then MGH is the way to go. Are there other kinds of potential energy? Well, the main example we use is gravitational, but there are other things. Here's another one that we'll talk about. We could talk about potential energy being 1/2 kx squared. This is the potential energy of a spring. So K is the so-called spring constant. And what's the force for a spring? This is for the force is equal to minus kx. This is Hooke's law. Hooke's law this is the spring force. That's the potential energy due to a spring. X is equal to 0 when you're at the equilibrium point for the spring. And you can either compress the spring or stretch the spring. Either kind of compression or stretching does what? It stores potential energy in the spring. What happens after you let the spring go, either after compressing it or stretching it? It then does what? It runs away, yeah. Well, not really, just a little bit, but then it runs away, but then it comes back. It runs away, then it comes back. It's a spring. It springs. Here's a picture. So you could take a mass, attach it to a spring with spring constant K. In here somewhere, you've got x equals to 0. As my picture is currently drawn, I'm drawing, let's see here, this distance right here is x, okay? To the center point of the mass. So as my picture is currently drawn, my current illustration, that spring is stretched. What's going to happen if you let it go? The spring is going to pull the mass back, right? And then the box is going to keep going. It's going to compress the spring a certain distance. And then the spring is going to push back, and the box is going to push back out again, and back and forth forever and ever, assuming what? Assuming no friction, right? Now, if there's friction, that's another story. Okay, so let's start by talking about the no friction case. These are our main contestants in the story of potential energy, all right? Gravity and springs. So what's the big idea of the energy method? It's just that for a conservative system, energy is conserved. Conservative system, energy is conserved. Now, that probably just seems like word soup to you. What does conserved mean? What's conservative politics? It's debatable, right? But the usual meaning of this term is you want things to remain the way they are. In other words, you don't want things to change, which is going to be wrong if you're a conservative and you want things to change, right? So you can't really, this term as it interfaces with your idea of politics in America doesn't quite make sense, probably for you, if you're like me and you consider yourself a conservative but you'd like to see things change, right? But the use of the term conservative in physics means that it's staying constant in time, would be a better description. Energy is constant in time. In physics, when we have something that's constant in time, we say that it's conserved. All right? So that's the energy method. We have conservation of energy. So to solve a physical system, what we got to do is look at it, identify what's the kinetic energy and what's the potential energy before and after the events take place, set them equal, and that allows you to solve problems. No free body diagrams, no components of vectors for the most part. Yeah. I'll find a way to bring trigonometry into it, though. Don't worry. I know. Like, you don't have to. Let's look at an example. So let's rework some of our examples that we've worked before. Mr. Top Hat has a ball, and he throws it upward with an initial speed of v0, right? Supposing that it is thrown from an initial height of h0, right? So you throw the ball from height h0 with initial speed of v0. So here's my questions. One, how high? Two, what is speed when it hits ground? All right. So let me just draw another picture to try to get the point. There are three events that are going on here, right? 3 different times. Time 1 is the initial thing that we're given, right? You've got m here. It's at h0, and you've got an initial speed of v0. So this is event 1. What's event 2 that we're interested in? So Mr. Top Hat's still down here, minding his own business, right? The ball is at the zenith of its flight, at what we have before called h max, right? You're like, hey, I got a formula for that. That's true. You have a formula for it. Great. But let's understand where that formula comes from using energy principles. All right? So what about the velocity at event 2 when it's at the top of the flight? Yeah, v top equals to 0, right? What's event 3? Yeah, when it falls to the ground, right before it hits the ground, right? It's got a velocity vf, and the question is, what is that, right? The question here is h max equals what, yeah? What's the final height? What's hf? Zero, right? The final height of the ball is 0. We're essentially just treating the ball as if it's a particle. So we don't know how big the ball is. We don't really care if it's a beach ball or if it's a baseball. The details of the size of the ball and which part of the ball hits the ground first, that does not matter to us in our thinking, okay? If you wanted to care about those things, you could, but then it wouldn't be a Physics 201 question. It would be something you're doing for a job, right? People should pay you money to do that problem, is my point, right? Okay, so energy is conserved. So what's energy 1? E1 equals to what? We've got 1/2 mv0 squared. That's my kinetic energy. What's my initial potential energy? mgh0, yeah? Now I could give you numbers for v0 and I could give you numbers for h0, but I think that's actually kind of beside the point, right? If you want, we could put v0 equal to 10 meters per second. We could put h0 equal to 2 meters, but then your top hat would be pretty tall. So I don't know. I'm going to leave them variable. We'll put numbers in the next example, okay? I promise. So how about event 2? What's energy 2? What's the kinetic energy at the top? So what's the kinetic energy of this marker right before it starts coming back down? It's 0. Ah! Okay, so no kinetic energy, and we just have what? mgh max, yeah? So the energy is purely potential there. And how about energy 3? Now, in the third case, we have 0 potential energy, right? It's all kinetic. So we have 1/2 mvf squared. And the conservation of energy, what does it say? It says E1 equals E2 equals E3. That is way easier than what we have been doing, right? I'm not like, well, there's the vertical and there's the horizontal, and no, I mean, it's just, well, okay, fine, this is a one-dimensional problem. My analogy is not a very good one. So if we set these equal, what do we get? You notice we can cancel the m, and we get h max is what? We get, if I can do the math, 1 over g times 1/2 v0 squared plus what? Plus, I'm sorry, let me, whew, all of a sudden. All right, so doing the math, I believe what I get here is v0 squared, man, this marker's pathetic, divided by 2g plus h0. Right? That actually makes a lot of sense, right? Because v0 squared divided by 2g is how high the ball would be thrown from where it leaves our hand, just on the basis having initial speed v0. And then since we're starting at h0, we just add that. The answer makes a lot of sense to me. I divided by mg to get that. So that answers part 1. How about part 2? For part 2, we want to have what? Mg h max equal to 1/2 mvf squared. No, I mean, we could do it that way, yeah? I guess that's true. E2 is equal to E3, so we could do it that way. You could set E3 equal to E1 if you'd rather do that. I mean, however you want. Since I did this, I'm saying I'll stick with this. This was E2 equals to E3. And so we got m's cancel, and we got VF is the square root of twice g times the h, the max, yeah? And then you can plug in what that was, right? So we've got 2g v0 squared divided by 2g plus h0. We could simplify that formula, right? But let me put one, so anyway, I do want to simplify this a little bit. This is VF equals to the square root of, how's that go? v naught squared plus 2gh naught, apparently. It's kind of neat. So you're like, well, why don't you put numbers in, right? Well, there's certain advantages to working a problem like this without putting numbers in. One of the things is we could think about what happens when v naught's equal to 0. What's this problem become if v naught's equal to 0? V naught equals to 0. We're just dropping it, right? So how fast did the marker hit the floor? Vf is the square root of 2gh naught. So if I drop a marker from 2 meters, which is about here, that should be hitting the floor, ignoring friction, at the square root of 2gh naught. Whatever that is. I'll tell you in a second. Oh. Yeah. So about 6.2 meters per second. So v naught equals to 0, h naught equals to 2 meters. Then we get Vf is about, square root of 2 times 9.8 meters per second squared times 2 meters, which I just calculated is about 6.261 meters per second. Let's see here. So here's another pretty standard example. You've got a building, all right? Completely unnecessary amount of detail in building. And suppose you've got a baseball, and you've got a batter who, every time he hits the ball, he hits it with the same speed. So you got a baseball batter, and he hits the ball up here at speed v naught, and let's say it's equal to 30 meters per second, right? Then you can ask the question, how fast, right, does the ball hit the ground? With what speed does the ball hit the ground if we launch it at angle theta? And typically, and let's suppose that the height of this building is 100 meters. Pretty tall building. Those are really big windows. So here's the question is, what speed does the ball hit the ground? And if I want to be nasty, I'll say, what is the dependence on theta? And I say I'll be nasty because that's a trick question. We're about to find out that there is no dependence on theta. Now, you could work this problem without energy methods. What would you do? You can write down the kinematic equations. Yeah? You can see, as a function of theta, how much time it takes for the ball to come back down to 0, right? You can figure out what the final y velocity is, what the x velocity. The x velocity is to be constant, right? And then the speed is the square root of vx squared plus vy squared square rooted, right? And after you work through all of that, you'll find out what we're about to derive in about 2 minutes. Which is why I did not assign this problem to you yet, I think, right? Was this in the recommended homework? See, for 231, I would definitely recommend this just because I like to, stick it to them a little bit. They're engineers. They're supposed to do that stuff, right? But this is a gen ed requirement for you guys, so I try to be friendlier. The point, though, is simply this. We have two events, the initial event and the final event, right? And so what we have is that the energy initially is equal to the energy finally, right? So where do you think we should make potential energy be 0? You say the top of the building? No, I refuse. That's some high quality trolling right there. That's not bad. That's not bad. I've been looking for that kind of sarcastic response in my math classes these many years, and I so rarely get it. Let's make potential energy be 0 down here, yeah? At the ground level. He's right, though. He could make it 0 at the top of the building. Then the potential energy would be negative at the ground if we did that. Some of you are already confused, so I don't want to do that. That would just add to the confusion, which is why I say he's being a troll, although a respectable one. Let's see here. But we like trolls. Let's see here. You got to have your own trolls, right? So what's the initial energy? 1/2 mv0 squared plus mgh0, because initially we got potential energy. mgh0, we got initial kinetic energy, 1/2 mv squared. And what's the story at the end? 1/2 mvf squared. Now, some of you have too much reliance on plugging numbers in. So you were a bit confused on certain questions on my test because you thought you needed to know the mass. When maybe you don't, right? Maybe you don't. Like this one, you don't need to know the mass. It's irrelevant. See that? Because at this point, mass cancels. So not knowing the mass does not make this problem unsolvable. In fact, it's fine. The answer to this question is independent of the mass. Now we just put in the numbers, right? So we've got cancel the mass. 1/2, what's my initial velocity squared? 30 meters per second squared plus 9.8 meters per second squared times, what was my h0? 100 meters, yeah? And that's equal to what? 1/2, the thing I'm trying to find, vf squared. I just divided by m. Now I would say we should multiply this by 2, yeah? So vf squared is equal to 30 meters per second squared plus 9.8 meters per second squared. Multiply the 2, I'll bring it into the 200, yeah? So vf is the square root of whatever that is, what, 900 plus, I don't know, 19.6? Is it 1960 meters squared per second squared? Doo-doo. Yep. Yep. Uh-oh. Oh, no. Oh, I multiplied by 2.
Yeah, but now it says 200 meters.
Yeah, that's the 2.
Yeah, but if you said you multiplied out the 2, then
Okay, so
is that, okay.
but that 2 times 100 times 9.8 is 1960. So we agree. We don't disagree. And so VF, I get 53.48. Meters per second. This problem, if you attempted it in our previous way of thinking is far more technical. I hope you see it's not that bad a problem with energy methods, right? And what's the theta dependence, right? Do you see the theta dependence? Is there a dependence on the angle? That's the neat thing. No, there is not, right? And how does that happen? Well, if I took theta really, really large, right, then I would just do something like that, right? So my final velocity would be something like this, yeah? And as you study different angles, somehow the length of the velocity vector is always the same. It's more or less vertical as you go over, because if you choose a shallower angle, more of your velocity is in the x direction, but it hits the ground in the vertical sense less, not as fast in that way. But it's in such a way that this, the length of the square root of vx squared plus vy squared is constant no matter what your choice is. The vf, this final speed, is 53.48, independent of the angle. Now, if you ask the question, what's the final x velocity for different choices of theta, the answer would be, well, yeah, there's a different dependence. For vx, what's vx? Vx is v naught cosine theta, yeah? And since there's no acceleration in the x direction, that would be it. Forever and ever, right? But that wasn't the question. The question was, what speed does the ball hit the ground with? Right? So. All right, so those are good entry-level questions. Let's bump it up a notch here. Inclined planes. All right, so suppose we've got this inclined plane. It's got a pulley. And so we've got a mass M1 here, string M2 over here, like that. And now we need a question. So let's see. How about this? Initially, M1 is distance h equals to 10 meters. This is a really big plane above the ground, all right? And let's suppose that M1 is equal to 500 kilograms. And let's suppose that M2 is equal to 100 kilograms, right? Let the angle theta here be 30 degrees. All right? So the question is this: if the system starts from rest, what speed does M1 hit the ground with? So, okay, in order for us to avoid that pesky, our pesky old nemesis friction, let us assume frictionless, all right? The pulley is massless. The string is stretchless and massless. So, I mean, lots of assumptions, but fine. Okay, so what we want to do is we want to say energy initial is equal to energy final, right? And what's a snapshot right before it hits the ground? My inclined plane all of a sudden got a steeper angle. Sorry about that. Right. So this final velocity right before it hits the ground, what's the velocity that the other box is moving with as well? Like, the string does not stretch, right? So whatever the speed M1 is falling with is the same speed that M2 is going up the plane with, right? So there's kinetic energy, not just for M1, but also for M2. So as we think about the final, the final situation, we've got kinetic energy in both boxes, right? In the initial situation, we've got kinetic energy in neither box because we let it go from rest. So that's the situation with the kinetic energy before and after. Now I got to think about potential energy before and after. How about potential energy? I think, so you probably would tell me to put H equal to 0 like here, right? Just to mix it up? Yeah, let's not do that. I'm going to put H equal to 0 here. Ground level, yeah. So, oh, interesting. I did not give us the height of M2. Does it matter? Does it matter? I would tell you it does not matter that we were not told where M2's initial position was. What we need to do is to give a label to it and work with that label, right? To deal with we have just give a label to your ignorance and you just deal with it, yeah? So what I'm going to say is that the initial position of M2 is at, let's call that H2, comma 0. And let's say that the final position of M2 is H2, comma final, all right? In contrast, H1, comma final is 0. And this is H1, comma initial. All right? Just let's give labels to the final and initial heights where the masses are. So with these labels set, now I can write potential energy plus kinetic energy is equal to potential energy plus kinetic energy, and we can see where that takes us. So initial energy, again, no kinetic energy initially, because it's from rest, yeah? Initial potential energy, we have M2, H2, comma 0. I forgot my G. G. Plus M1, H1, comma 0. I keep forgetting my G. All right, we do know that H1, comma 0 is 10. I'm just not putting that in yet, okay? We know that value. I'm just going to leave it symbolic for a second. And what's the final energy? Well, we've got 1/2 M1 VF squared plus 1/2 M2 VF squared, right? We've got kinetic energy in both of the boxes at the final time, right? They're both moving. And how about kinetic potential energy at the final time? Well, we've got plus M2 G H2F, right? And on the other hand, the potential energy of the first mass is 0 at the end, right? So this is energy conservation. What can we do with it? We can't just cancel masses this time, can we? Because we have different masses, right? I can't just divide by M1 or M2. That masses stay, much like the Atwood machine you guys are playing with this week in the lab. Right, so what do I know, what don't I know? Let's see here. So we could solve it like, let's isolate what we're after, which is VF squared, right? So we've got 1/2 M1 plus M2 VF squared equals to what? We've got M1 GH10, which we know, and then plus M2 GH20 minus H2F. So what I did was I just solved, I grouped, these two terms are coming from this guy and also that guy. Let me draw a different picture. There's a geometric aspect to this problem that you have to see, otherwise you're just going to be stuck at this point. All right, how to say this? Maybe I can draw it on the original pictures, right? So there's 2 points that are interesting. Let's say this point is Drake. All right, and so here's Drake on my other diagram. All right, there you go, Drake. And then there's this other point up here, right? We need a name for that point. What do you want to call it? What? Sorry? What? Oprah? Oh, okay. How do you spell that? Like that? I don't know. Is that opera? Is it Oprah? I don't know. You know what? I'm going to go with Opie. There we go. That's probably also misspelled. Hey, wait a minute. It's a name. You can spell it any way you want, right? Like, I regret. I was thinking about it. I named my son Benjamin. I should have named him this. Right? And then he could have been saddled with the responsibility of telling people, no, it's spelled that way. My parents are idiots. I lost my chance, though. It's already set in stone. It's like the regular spelling of Benjamin. It's no fun. Anyway. So my point to you is if you look at this distance here, so I'm trying to draw these points down here again in its own, little picture. What's the distance between Drake and Opie? If the string doesn't stretch, how far is that? How far did the mass fall? Yeah? 10 meters, right. So that means that this distance is 10 meters. So what in this picture, what is the significance of this over here? Like, what's this? Look at that. That's H2F, right? Minus H1F. Agree? Because that's how far the box went up the thing, because that's how far the box fell down. Because the string does not stretch. So what's the change in height for the box which is on the incline? It's not 10 meters, right? It's less than that. This angle was given. It's 30 degrees, right? So this should be 10 meters times the sine of 30, otherwise known as 5 meters. So if it's a 30-degree slope, that means that the box on the incline only went up 5 meters, while the other one fell down 10 meters. Different angle would give you different, proportion. But my larger point is that this, why do I want 2's and 2's. I'm an idiot. H2F minus H, that's supposed to be H2I. Don't let me, guys, don't let me sell you on that. Come on, H2. Oh, I'm using 0 or am I using I? What am I doing? 0. 0, 0, 0. I'm sorry, I either use 0 or I. This is for initial, I don't know. I'm just warning you, I have a default, when I label the initial event, sometimes I call it the 0th event, so I put like sub knots on it. Other times I put sub i's on it because it's the initial event. Just beware, that's me my default labeling. I don't even think about it. I just do it by accident sometimes. Okay, so this is 5 meters. What do we have underlined in green over here? See it? It's turned over. That's minus 5 meters. So not the whole thing, but this right here is minus 5 meters by this discussion. And we know everything, right? So all we got to do is VF squared is 2 divided by M1 plus M2 times M1G H1 naught plus, well, rather minus M2G times 5 meters. And you can plug in the numbers. So we got 2 over what? 600 kilograms. And what was my M1? 500 kilograms times 9.8 meters per second squared. Of course, you could have factored out the G. What was my initial height? Oh, 10 meters. And then I've got minus, what was M2? 100 kilograms times 9.8 meters per second squared times 5. And you got to crunch these numbers. And after you crunch these numbers, you still haven't found the speed, right? You found the speed squared. So after all that's done, you still have to take the square root of this. So I'll take a minute to do it. Agreed. I get 147. And then I got to square root that. Which is 12.12. Now, again, I could have asked you this question on test 1, right? But I didn't, because I thought, if I'm going to ask this question to you, I might as well ask you this question on test 2, where you can work it in a nice way, right? If on test 1, you'd have to figure out the acceleration. You got to look at the free body diagram on each of them, work out the tension, eliminate the tension, find the acceleration, work through the kinematics, figure out how much, blah, 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 blah. This is much easier. Like the really hard part here, I think, is realizing that you have to relate the distance that the box falls to the distance it goes up the plane, and then understand that that means that the potential energy changed for M2, it's not 10 meters, but instead 5 meters that leads to a change in potential energy for M2. And we can summarize what happened here as follows, which is that M1 drops, right, converting its potential energy into kinetic energy. But as it does that, it pulls M2 up the plane, right? And that requires adding potential energy to M2. And that's why, if M2 wasn't in the picture, and we just dropped M1, we could go back to my first example. We could just do the square root of 2 times g times 10 meters, right? We'd revert to that formula again. So let's do another example. Wait a minute, is this 4? I don't know. 4. All right, so you have Cannon.